In today's lecture, we are going to look at a problem on combined loading. So this will be the first problem that we will be looking at combined loading. And later on, we'll probably look at maybe one or two more examples in the course. Okay. So what are today's objectives? So by the end of this lecture, you will be prepared to do two things. One is you will be able to construct shear and moment diagrams for structures under combined loading. Okay. This is a little different from what you did for your 213. And the second thing, which is probably the most important thing that we'll learn today, is to determine whether the moment diagrams that we construct have the correct sign for the given coordinate system. Okay, let's look at the problem now. Okay, so this is a shaft that has two pulleys, and there are different forces acting on these pulleys. And what the problem asks us to do is to find out the locations of the highest tensile, compressive, and shear stress in the shaft. So what this means is that you essentially have to look at the entire length of the shaft and figure out at what location along the x-axis here that we have the maximum bending stress and the maximum shear stress. Okay? And for that, essentially we have to construct shear and moment diagrams and then find out where the resultant moment is maximum and then figure out what is the maximum bending stress. And the other thing that is important is also to figure out exactly at which point in that cross-section you have the maximum tensile stress and at which point you have the maximum compressive stress. Okay? So in any problem like this, the first step to do is essentially to determine the reactions, the support reactions. So in this case, you have a solid shaft which is simply supported at A and D, which means that there are going to be no moments or moment reactions at A and D. Okay? And because in this problem you don't have any forces in the x direction, you also have zero forces or zero reaction forces in the x direction at both A and D. Okay? So the first thing that we're going to do is determine what are the reactions that we actually have at A and D. And based on what we know from the problem, we know that there are going to be only two reactions. One is going to be a reaction in the y direction and a reaction force in the z direction. Okay? And these are the reaction forces at the two supports, but the shaft itself is essentially going to experience bending moments. Okay, there are going to be two bending moments, my and mz, okay? And there is also going to be a torque, mx, that is acting along the axis of the shaft because of the uneven force in the two pulleys. So if you look at the pulleys here, one of these pulleys, the pulley B, for example, has a force of 1,000 pounds on one side and 200 pounds on the other side. So essentially the forces are unbalanced, and because these forces are unbalanced, you're essentially going to have a torque. Okay? But let's just first start with finding the reactions at A and D. Okay? So before we start the process of finding the support reactions, let's just make sure that we understand the coordinate system that is there in this particular problem. Okay? So if you look at this problem, you essentially have let me just draw it here. So you have the x direction going that way and the y direction going up. Okay? So if you look at the coordinate system, x is going to the right here and the y is going up. Okay? And the z is coming out of the plane. Okay? So this is the coordinate system that you're operating with. And now we are first going to look at the xy plane. Okay? Now, if you look at the xy plane, there are actually three forces. Okay? There is a force at D, which is a reaction force. Let me call that dy. There is a reaction force at A. Let me call that ay. In the pulley at B, you don't have any forces in the y direction. You only have forces in the z direction, so we don't have to worry about that pulley. But at pulley C, though, you do have forces in the y direction. And those forces, in this case, are actually acting downwards or in the minus y direction. So the net force that is acting at point C is 600 pounds, and that is acting in the minus y direction. Okay? So this essentially is the free body diagram for this particular shaft in the xy plane. Again, I want to remind you that we are looking at the xy plane, so we don't have to consider forces that are acting in the z direction. Okay? And now, once we have this free body diagram, we can essentially find out what the reactions ay and dy are essentially using force and moment equilibrium. Okay, so the first thing we can do is we can say sigma Fy is equal to 0, which basically implies that Ay plus dy should be equal to 0. Okay, sorry, Ay plus dy should be equal to 600 pounds, okay, which is the force in the minus y direction. Okay, so that is the force equilibrium equation. Now we can do moment equilibrium. So we can say the moment, okay, along the z direction, and we can take the moment about any particular point that you want. So we'll just say that we are taking the moment about point A, that is equal to 0. And if you look at the moment equation, then essentially you're going to have a moment due to the 600 pound force, and you're going to have a moment due to dy. The moment due to Ay is going to be equal to 0 because we are taking the moment about that particular point. Okay, so then you do that. So 600, okay, that is the force, and we know that this distance is 20 inches and this distance is 10 inches. Okay, so 600 times 20 should be equal to dy times 30. Okay, and if you do that, you will find that dy is equal to 400 pounds. And once you find dy, you can find Ay is equal to 200 pounds. Okay, so what you have done is now finding out the reactions in the y directions at the two supports A and D. Okay, now what I'm going to do next is essentially do the same thing for the xz plane. Okay, so again, if you look at the xz plane here, we will assume the reaction forces at point A and point D to be in a particular direction and see whether our assumptions are correct or not. Okay, here before we go any further, I want you to pay attention. The way we define the coordinate system in the xz plane is by looking at it from the top. So that is the direction in which we are looking. Okay, so now if you look at this particular shaft from the top, what you will see is that your x is going to the right, your z is pointing downwards, and your y is coming out of the plane. Okay, so this is something that is important. When you are given a coordinate system for the problem, you have to use that. You can't use a different coordinate system. Okay, if you choose to use a different coordinate system, ultimately you have to come back to the initial coordinate system. Okay, so now given that this is the coordinate system, what I'm going to do is I am going to assume that the reaction forces at point A and point D are in the positive z direction. So I'm going to put my AZ downwards and my DZ downwards. But remember, this is the positive direction of z. Okay, and we also have a force on the pulley B that is in the positive z direction. Okay, and the total force at point B is 200 plus 1000, which is 1200 pounds. Okay, and that is acting at a distance of 10 inches from point A. Okay, and the distance from point B to point D is 20 inches. Okay, so once we have constructed the free body diagram for the xz plane, we can again use force and moment equilibrium to find out what are the reactions AZ and DZ. Okay, so again, sigma Fz is equal to 0. That implies AZ plus DZ is 1200, or actually is equal to minus 1200. Okay, because AZ, DZ, and the 1200 pound force are all in the same direction. Okay, so then you would have AZ plus DZ plus 1200 is equal to 0, which means that AZ plus DZ is minus 1200 pounds. Okay, and then we can also do a moment equation. We can say My about point A equal to 0. Okay, here I want to again pause for a minute and remind you that the moment caused by AZ, DZ, and the 1200 pound force are going to be in the y direction. Okay, not in the z direction, not in the x direction. Okay, if the forces are in a particular plane, then the moment caused by forces is going to be on a plane that is perpendicular to it, or a direction perpendicular to it. Okay, so it's going to be My, not Mz or Mx. Okay, so you have sigma My about point A to be equal to 0. Then we do the same thing, which essentially implies dz times 30 plus 1200 times 10 is equal to 0, which essentially means that your dz is equal to, let me have the value here, is actually minus 400 pounds. And based on that, your AZ is going to be minus 800 pounds. Okay? So what you have done so far is essentially find the reactions at point A and point D. Okay? And once you find the reactions, then we can construct our shear and moment diagrams. And that is what we are going to do next. Okay? So this is going to be the place where we're going to find the shear and moment diagrams. First, we're going to look at the XY plane, okay? And then we will look at the XZ plane, okay? So just to go back, we found that the reactions AY and DY to be equal to 200 pounds and 400 pounds here, okay? So I'm going to use those values for this particular construction of the shear and moment diagram. So this is DY, and that is AY, and AY is 200, and dy is 400, and everything's in pounds. Okay, and we are using the same coordinate system that we started with. X is pointing to the right, y is pointing upwards, and z is pointing out of the plane. Okay, and we also know that there is a force of 600 pounds at this point. Okay, so this is 20 inches, and this is 10 inches, and this is point C. Okay, so once we have the free body diagram, it is fairly easy to construct the shear and moment diagram, and this will be shear By, okay, and it is going to be in pounds. Okay, and once you have the free body diagram, the way to construct the moment, the shear diagram is fairly simple. So you look at the initial point, you essentially have a 200 pound force, Ay. So essentially your Vy diagram starts at 200 pounds, okay? And as you go along the axis, there are no external forces all the way from point A to point C. So the shear diagram is essentially going to be a straight line till point C, okay? And at point C, you have a 600 pound force acting downwards. So there is going to be a jump of 600 pound force there, okay? So this is going to be 200, okay? And you're going to have a jump of 600 or minus 600. So you are going to minus 400 here, and you stay there all the way until you get to D, and then again there's a jump of 400 pound force there. So this is going to be minus 400. Okay, so that is going to be your shear diagram. And once you have the shear diagram, you can construct the moment diagram. Again, this moment, just to remind you, is not mx or my, it is actually mz. Okay, and mz is in pound inches, because those are the units that are given in the problem. Okay, so again, this is x-axis, just to remind you. This is in inches, and this is x, again in inches. Okay, so now once you have the shear diagram, the moment diagram, I'm pretty sure all of you know how to do it. So essentially you start with moment equal to 0 here, because you have a simply supported shaft. Okay, when you have a simply supported shaft, at the supports, you essentially have 0 moments. So you start at 0, then you have Vy equal to 200. So essentially you have a positive slope for the moment. So you keep going at the rate of 200 pounds. Okay, you go up to the point C. Okay, and at point C, you essentially have a change in the shear, which means that the slope of the moment is going to change, and it's going to go from positive 200 to minus 400. So from this point on, it's going to go down, go down, go down, and then till it reaches 0 at point D. Okay, so this is going to be 200 pounds here. That is the slope, which means that this is going to be 200 times 20, which is actually 4,000 pound inches. Okay, so that is your maximum mz, and that occurs at point C. Okay, so that is where we are. Okay, so this part, up to this part, it's actually very similar to what you have learned in your solid mechanics class. Okay, so you have usually done shear and moment diagrams in 1D, and this is where you would stop if you are in your solid mechanics class. Okay, but this class we are going to look at bending moments in 2 dimensions. Okay, And one of the important things that you must know is whether the sign of the bending moment that we get from this moment diagrams is correct or not. Okay? So this is the conventions that you used in your solid mechanics class and you have got so far. But here we have to check whether the moment that we got has the right sign. The magnitudes are correct, we know that. But the signs may be wrong. So we want to make sure that the moment diagram has the correct sign. Okay? And that is what we are going to do next. And how are we going to do that? So what we are going to do is, we are essentially going to choose any one point along the shaft. Okay? It could be some point between A and C or C and D, for example, it doesn't matter. Okay? You're going to choose some point, okay, and then take a section at that point, isolate the free body, and then find out what is the moment, the internal moment at that particular point using your free body diagram. Okay? And then check whether the moment that you get from the free body diagram is the same as the moment you get from the moment diagram. If they are the same, you just stay put. There is nothing to change anymore. The moment diagram is correct as it is. But on the other hand, if you get the opposite sign for the moment based on the free body diagram, then you will have to flip the moment diagram. Okay, so let's just check out at this point. So what I'm going to do is, I'm going to choose some arbitrary point. Okay, let me go to the next slide. So I'm going to choose some arbitrary point. So this is point A, and this is point C. And this is where you have the 600 pound force. Okay, and this is where you have the 400 pound force, and this is where you have the 200 pound force. Okay, so I'm going to choose some point, a distance x from point A, and I'm going to draw the free body diagram for that particular segment. In this case, I'm going to choose the left segment. Okay, so if I do that, let's look at the free body diagram. You have the 200 pound force here. That is the reaction at point A. This has to be counterbalanced by an internal shear force, okay, of 200 pounds. Okay, and remember, this is at a point or a distance x. Okay, now if you look at the equilibrium of this body, the particular body is not going to be under the equilibrium under the 200 pound forces that are acting on the left and right. There has to be an internal moment to counterbalance the rotation. Okay, so now if you take the moment about point A, this 200 pound force here is going to cause a clockwise moment. That has to be counterbalanced by an internal moment acting at the cross section. So that internal moment is going to be in the counterclockwise direction, and that my is going to be equal to 200 times x. Okay? Now, what you know is we don't even have to worry about what the actual value is. We don't have to look at a specific value of x or so on. All we need to know is what is the sense of the moment. Okay? Now, if you look at this my, if you use the right hand rule, essentially curl your fingers along the direction of my, and what you're seeing is that my thumb is pointing towards me, which is the direction of z. So what it's telling you is that the internal moment, I made a mistake here, it should be actually mz. Okay? The internal moment in this particular cross section, mz, is along the positive z direction. Okay? And if you go back and look at the moment diagram that we constructed, we see that for any point between A and C, mz is positive. Okay? So the moment diagram says that the moment should be positive at any point between A and C, and our free body diagram also says that the moment between any point A and C is positive, which means that our moment diagram is correct as it is. We don't have to do anything. Okay? So we are good. Okay? Now we are going to do the same thing for the xz plane and see whether in that particular case whether we can keep the moment diagram as it is or whether we will have to flip it. Okay? So for that, first I'm going to construct the shear and moment diagrams in the xz plane. Okay? So if you look at the xz plane, you have a 800 pound force here at point A, and you have a 400 pound force here at point D. Okay? Remember, we got AZ and DZ to be negative, which means that they're actually in the minus Z direction, not in the positive Z direction. And remember, positive Z is downwards. So that's why AZ and DZ are pointing up. Okay, so we are consistent with the sign, we are consistent with the values that we got before. Okay, and we also know that there is a force of 1200 pounds at point B here. Okay, so this is our free body diagram for the XZ plane. And based on that, we can construct our shear and moment diagrams. So in this case, this is going to be VZ. Okay, it's going to be in pounds. This is X in inches. And what you see is that we have an 800-pound force acting in the minus Z direction here, which means that our VZ is going to start at minus 800. Okay, so it's going to be minus 800 till we reach point B. At point B, we have a force in the positive Z direction, which means that there's going to be a positive jump. Okay, so we're going to go from minus 800 all the way to plus 400. Okay, so this is going to be minus 800, and then we are going to plus 400, and then that is going to remain all the way until point D, where it's again going to come back to 0. Okay, so this is going to be 400. Okay, so that is our shear diagram. Okay, in the XZ plane. Based on this shear diagram, we can construct the moment diagram. So the moment here, again, as I mentioned before, it's My, and that is in pound inches. Okay, and based on the conventions and the formulas that you learned earlier in solid mechanics or some other strength of materials class, we know that from the VZ diagram, it's fairly easy to construct the moment diagram. In this case, we have 0 moment at point A because it is simply supported beam. And from that point on, we are going to have a negative slope because VZ is negative. So we're going to go down at the rate of minus 800. Okay, and then once you get to point B, there's a change in slope of the moment because your VZ now becomes positive. So then we are going to go all the way up to point D, where it again goes to 0. So this is going to be, this point here is going to be minus 800, that is the slope. Okay, so minus 800 times, this is 10 inches, and this is 20 inches. So you're going to have a value of minus 8,000 pound inches at point B. Okay, so this is the moment diagram based on how we had constructed moment diagrams earlier, probably in your 213 or your solid mechanics class. Okay, so this is just saying that dm over dx is v. That is all we are doing here. Okay, but now we have to check again whether this moment diagram is correct. More precisely, whether it has the right sign. Okay, and that is what we are going to do again. And this time we are going to choose some section between A and B. So what I'm going to do is I'm going to take a section somewhere between A and B. Okay, that is what I'm going to do. And I'm going to isolate the free body and then look at the equilibrium of the free body. Okay, so if you look at that, so you have, just to remind you, this is an 800-pound force here, there is a 400-pound force here, and there is a 1200-pound force here. Okay, and I'm going to take a section somewhere in between point A and point B. Let me call that distance x. Okay, and now I'm going to look at what is going to be the internal moment at that cross section x. Okay, so if I do that, I construct a free body again. So you have an 800-pound force this way, okay, which has to be counterbalanced by a shear of 800 pound. Okay, and to make sure that the body does not rotate, you essentially have to have a moment my in the counterclockwise direction again. Okay, and this moment my is going to be nothing but 800 times x, because this distance is x. Okay, so now we have a problem, or it's not a problem, we actually have found something new. Okay, this my is a positive my because it is in the counterclockwise direction, and if I curl my fingers in the sense of the moment, my right thumb is pointing towards me, which is in the positive y direction. Okay, so the free body diagram tells us that the moment my at any point between A and B is actually positive. But if you go back and look at the moment diagram we constructed, we see that the moment is actually negative between A and B, based on the moment diagram. The question is, which is correct? The answer is, this is correct. Okay? Because this does not assume any conventions. This is simply based on force equilibrium, okay, and moment equilibrium. Okay? There's no conventions. And this tells you the moment my at any point between A and B is actually positive. Okay? So this is correct. So all that we need to do to make sure that the my diagram that we constructed previously is correct is essentially to flip it about the x-axis. So instead of having it go down like this, all we need to do is essentially make it go up like that and go down. The values and everything is still the same. So this is going to be, instead of minus 8,000 pound inches, it's going to be plus 8,000 pound inches. Okay? That's the only thing that is different. So you just mirror whatever moment diagram you had before about the x-axis. Okay? And the reason that you're doing this is because the moment that we got from the free body diagram is of the opposite sign from the moment that we got from the moment diagram directly. Okay? So this is the correct moment diagram. So this essentially tells you that the my along the x-axis throughout the shaft is actually positive, not negative, as our bending moment diagram indicated. Okay? And the reason that we had this conflict is because if you remember what you learned in your solid mechanics class or any other strength of materials class, you essentially would have used the equation dm over dx is v. Okay? But that equation is true only for a specific coordinate system. Okay? Generally, dm over dx, the magnitude of that is equal to v. But dm over dx can be either positive v or negative v, depending on the coordinate system. In the xy plane, it turned out that your dmz over dx is actually vy. But for the xz plane, dmy over dx is actually minus v of z. That is why we have this conflict. Okay? So to make sure that we don't get astray because of this issue with the sign, you always want to make sure that you check the sign of the moment by drawing the free body diagram for any point, okay, for any particular section, and see whether the values that you get from the free body diagram and the values that you get from the moment diagram are consistent. If they are not consistent, all you need to do is flip the moment diagram. Okay? So this is something that is very important, because if you don't get the sign of the moment correct, then as we later determine the neutral axis will be wrong. Then the points where you have the maximum tensile stress and the maximum compressive stress, those will be wrong. So it is absolutely essential that we get the sign for the moments both in the xy plane and the xz plane correct. Okay? I hope that is clear to everyone. Okay? So now, the last thing that we are going to look at in this particular lecture is essentially pose a question. Okay? So we found our mz, okay? Okay? And we found our my, okay? Pound inches. And we have now made sure that both these moment diagrams are correct with the right sign. Okay? Now the question is, at which point along the axis of the shaft are we going to have the maximum resultant moment? Okay? We know individually what mz looks like as a function of x. We know what my looks as a function of x. We don't know how mr looks as a function of x. And it is mr that we have to maximize, because the bending stress depends on mr, not mz or my. Okay? Just to remind you, this mz diagram essentially looks like this, right? It goes on, keep on rising till point C, then it comes down to 0 at point D. So this is point A, this is point C, and this is point D, and you have a maximum of 4,000 pound inches at point C. The my diagram is a little bit different. The my diagram becomes maximum at point B, okay? And then it keeps reducing all the way to point D. So this is point B here, and this is 8,000 pound inches. Okay, so this is point A, this is point D, and this is somewhere point C. Okay, and this is somewhere here is point B. Okay, so now we have these two diagrams, mz and my. Okay, what we need to find out is where mr is maximum. Okay, so we will look at this in the next lecture, but I would like you to look at these two diagrams and think about how can I find where mr is maximum. Just to remind you, mr, the resultant moment, is basically square root of my square plus mz square. We know this, right? So how are you going to make sure that mr is maximum, and how are you going to find out the maximum value of mr? Okay, I want you to think about it, and in the next lecture we'll probably look at a couple of different ways to find out mr, both for a general case and for a case where you have only a linear moment diagram like we have here. So if you look at all the segments here for the moments, this is all linear. So you have a kind of a shortcut when you have a linear moment diagram to find out where mr is maximum. So we'll look at both the general case as well as the specific case for the linear moment diagram. Okay, and that we'll do in the next class. Okay, thanks for watching, and I'll see you next time.